Hello, everyone. I'm back, still alive. I'm definitely still running this podcast. Just a lot has changed. I'll keep it short. I got into graduate school, and I'm currently in week 4 of my PhD in psychology at Rutgers University. So I'm currently living a new life and thoroughly enjoying it, and will definitely use my geography as a benefit for my podcast. So stay tuned for that. But this video is not about me, and I may make a video related to graduate school sometime in the future. Who knows? With that said, though, let me introduce my guest, Prof. Stevan Harnad. There's a lot to say about my guest, so I will keep it short. Simply put, Stevan is a legend in the field of cognitive science and AI. Not only has he published seminal research papers examining categorization and categorical perception, his PhD dissertation titled The Symbol Grounding Problem is a landmark paper that introduced the idea that for symbols to have their meaning, the interpreters of these symbols must have a body. Without a body, one cannot feel. I was one of Steven's many undergraduate students, and I'm incredibly privileged to have worked with him for over a year. Not only did he train me how to think and be a better researcher, he also indirectly influenced me to pursue a career in cognitive science, a true passion of mine. For that, I am eternally grateful for. In this episode, which is now officially a year old, we go deep into the topics of cognitive science, categorization, linguistics, computer science, and ChatGPT, how it works, and whether or not it is sentient. Despite the age of this conversation, nothing in this video is outdated, and Stevan is one of the smartest individuals I know, and you will learn a lot from this podcast. And so, with all that said, here's my podcast episode with Professor Stevan Harnad. Dr. Harnad, thank you very much for taking time to do this. I really appreciate it. And before we get into your vast array of expertise and also historical expertise within the field of cognitive science, I was wondering if you could give us a background on your academic history and where you are right now, and how did it lead to where you are right now?
Okay, I did my undergraduate work in psychology at McGill and also a master's. Then I did a PhD at Princeton, and I started to do research on lateralization in the nervous system, or in the brain. And then I started a journal called Behavioral and Brain Sciences, which was for controversial topics in what we would now call cognitive science. And then I started to teach at University of Southampton, first in psychology, then in computer science. And then I came back to Canada on a Canada Research Chair at UQAM, where I still am. I came back in 2000.
You have this paper, which is my favorite paper in all of psychology, if I'm being very honest with you, which is to cognize is to categorize. Cognition is categorization. I was wondering if you could explain as to why you believe categorization is so important into our cognition, and also before we get into that, maybe tell us what categorization is in the first place.
Okay. First of all, as in many things, I've been wrong, and already when you were taking the course, I said that it's cognition. Cognition is mostly categorization, but there are things that we should be ready to call cognition that are not categorization. But first, let me say what categorization is. In some ways, it sounds too general. To categorize is to do the right thing with the right kind of thing. And that's a circular definition because kind means category. Mm-hmm. Okay, that's like saying to categorize is to do the right thing with the right category of thing.
Right.
But we know what it is to do the right thing with anything, and naming things, recognizing them, naming them, identifying them is the main way we do it. But it's not the thing the right thing to do is not necessarily to call a spade a spade. Yes, if you recognize spades and you call them spades, you're categorizing. But there are tons of other things you do with spades besides call them spades. For example, you pick them up and you shovel with them, right? And that's the beginning of the story. The way you ground the meaning of a word is first through your sensory motor interaction with the category to which it refers. If you open a dictionary, this is going to be boring for you because you've heard it before, but if you open a dictionary and you look at the words, 99% of them are category names. They're content words like nouns, verbs, adjectives, adverbs. You can point not only to apples and square and spades, etc. You can also point to more abstract things like that's good, that's bad, that's fair, that's not fair. That and those things become you can turn them into general nouns, saying all the things that are fair are what we mean by justice, and so on and so forth. So basically, those even abstract words are names of categories. They're far away from the from the example that I always use, which is the mushroom island, where you're marooned on an island and it's full of, and you're a vegan, of course. So the there's full of mushrooms, and mushrooms are vegan, but you don't know which ones are edible and which ones aren't. So the only way you can find out which ones are edible, with which the right thing to do is to eat them, and which ones are inedible, with which the right thing to do is to avoid them or throw them away, is to try a little bit, see if it makes you a little sick, and then by trial and error, if you're lucky, before you starve, you figure out which ones are the edible ones, and that's categorization, and that's what categorization is for, starting from mushrooms all the way up to goodness, truth, justice, etc., and the full power of language.
Okay. I just want to add like a clarification, if you can. It sounds like the way you described that categorization is a lot like learning. Is categorization only learning, or is there more to it than just that?
There are you have categories that you didn't learn, you were
Mm-hmm.
born with. You have feature in general. When you categorize, the way you do it is by features, and you can detect the features that distinguish the members of the category from the non-members. With mushrooms, it's simple, it's the edible ones and the non-edible ones. With a taxonomy of animals, it's the features that distinguish giraffes from zebras, from impala, from bears, etc. And and in general, the features have to be learned from experience, by trial and error, what's called supervised and unsupervised learning. But there are also innate feature detectors, and colors, the ones that I started with, are the famous ones. We learn to call red red, orange orange, and green green, etc. But we don't have to learn the features. And
Mm.
non-speaking animals also have those categories because they know the right thing to do with red things and green things, and they can tell them apart. So there are innate categories that you're born with, and that means innate category feature detectors, but most of them are learned. And that's another exercise with the dictionary. Not only are almost all the words in the dictionary category names, but almost all the category names are learned rather than innate.
Right. And how many categories would you say, or does the research corpus say, are actually innate versus learned? Because there's obviously the
I have
nativist empirical
I have
divide.
no idea. I have no idea, and not a well-defined question, because a lot of the innate categories are things that we don't name. They're just that we recognize, and we don't even give them a name. But I can give you numbers for something, which is how many categories do you have to ground directly by trial and error, and name them, so that from that point on, language can take over. But that I can tell you, but I can't tell you how many innate categories there are.
Okay, so then to learn or acquire categories requires more, or sorry, it requires a minimum amount of interaction with the environment, and then language takes over it after a minimal amount, that minimal amount,
But
right?
language can take over. I don't think it does completely take over. The way I used to put it in the course is that it's not as if once you learn the minimal grounding categories and their names, you go into a dark room and the rest of your life is just verbal. It's not.
Yeah, yeah.
Right? I mean, you're still going around seeing new things, and not just, in other words, the example that I use all the time. You could learn zebra from being told, if you know what a horse is and you know what stripes are and black and white are, you can be told what a zebra is in words. But you have to know what black, white, etc., means. But you may learn what a zebra is directly later in life too, without anybody telling you anything. So it's not. You can do it just verbally after you have a minimal grounding set, but you won't.
Okay. And I'm glad you brought up minimal grounding set. Could you explain what that is? Because I find it very fascinating.
If you take a dictionary, and this is, I like to do this in words rather than showing you a diagram. If you take a dictionary uh, and you don't know, in a language that you don't know, this is at the same time an example of the symbol grounding problem. In a language that you don't know, like a Chinese dictionary, what you can do, don't ask me how, but what you can do is you can pronounce the characters. So somebody says, what does ban ma mean? And so you know how to, and you can alphabetize it. So you get through the dictionary, you reach the word ban ma, and what do you find? And ban ma is a set of Chinese characters. What do you find beside it in the definition? Another string of Chinese characters. You can pronounce them, and you can look them up again, but you're not getting anywhere. You're just going around in circles because you don't know what any of them mean. So the minimal grounding set is how many words and which ones do you need to know already uh, in order to be able to learn all the rest of them from words alone. Banma happens to mean zebra. So zebra, and the definition of zebra is a horse with stripes in Chinese, right? So how many words in the dictionary do you need so that all the rest of the words, besides those minimal words, you can reach just by words alone? And the surprising answer is it's somewhere between 750 and 1500, which is very few. I mean, dictionaries have hundreds of thousands of words, can have hundreds, if you, especially if you include technical stuff. Do you want me to tell you how you find that out? It's also simple.
Absolutely.
Okay, so what you do is, in a dictionary, you can take all the words that are, by the way, what's a dictionary? Dictionary is a set of words in which every word in the dictionary is defined by words in a dictionary. And a definition is a string, it's a proposition, a string of words. And to simplify, it basically tells you the features of the defined word that define it. So with this definition of zebra is a black and white striped horse looking thing, right? So in a dictionary, you have every word is defined, but not every word by a word in the dictionary, but not every word goes on to define anything else. There's some tail end, there's sort of not dead ends, but ends that go no further. The example I usually give is pterodactyl, which is a flying dinosaur. Maybe I'm wrong. I never even checked whether a dictionary contains a definition of something else. I don't have to because we use a computational method to find it. Does the word pterodactyl is it used to define something else? Are there green pterodactyls and blue pterodactyls, and we call the green pterodactyls with one name? I don't know, but there are things, lots and lots of words in the dictionary that don't define anything else. You can make a graph out of the dictionary where you take the word that is being defined as one node, and then all of the words that define it as incoming nodes defining that word. And in that graph, you can see whether there are any words that get incoming nodes defining it, but they don't define anything else. And if you find one, you throw it out because you know you can get to it with what's left. And you keep doing that recursively. It's amazing. You can reduce the dictionary to about 10% of its size by removing all of these words already. But that 10% is still huge. It's not the minimal grounding set. It is a grounding set, but it's not the minimal grounding set. The minimal grounding set is within that dictionary. And I'm not going to bother you with any details over there. It's much smaller. You have to solve a problem called an NP-complete problem, a problem that is almost, except under unusual circumstances, not soluble at all. For oriented graphs, it's called the minimal feedback, finding the minimal feedback vertex set. You can't do that computationally, but you can approximate it with a few tricks that are not important for what you're saying. And we found that for all of the dictionaries that we tested, that we could find the size. I'm not really, you'll see why I don't want particularly the set, but the size. We can find the minimal size by graph theoretic analysis and computation. And then it turns out, that's the good news, you can find it, and it's very small, somewhere between 750 and 1500, depending on the dictionary. But the bad news is that there are many of them, all in the that first reduction is called the nucleus of the dictionary, 10% of the dictionary. They're all in the dictionary, and there are other structures in there which I won't bother you with, but there are many of them. Some of them are almost the same, just a few word differences, and some of them are more different. And so there's no point looking for the unique universal set of words that everybody has learned, and then everybody else did the rest of it in a dark room. They all learn different categories, a lot more than they really need for a minimal grounding set. But once you have a minimal grounding set, formally and logically, you can explain all the rest of the categories verbally. You don't have to do any more direct grounding.
Okay, awesome. Thank you for that explanation. It was really well done. How did you actually get a hint of how to like actually go into this direction of reducing the dictionary to this minimal set?
Well, actually, it was bumbling all the way. There was supposedly a dictionary called the Longman's Dictionary of English that had already done this analysis. It said this dictionary is for new learners of English, and every word is defined with just 2,000 control words. And we had a team of mathematicians and graph theoreticians get together, and we wanted to create the graph of that and then look at the structure of meaning, etc. But the mathematicians got disgusted right away. They said, this dictionary is not following its own rules. It's not, first of all, it's not a dictionary. It contains words that are not defined. Second of all, the control vocabulary doesn't define everything, and nothing in the control vocabulary is defined. So everything was wrong. But the mathematicians said, but we can make something true that is like that. And the method I described to you is the one that was used. We can obviously get rid of the words that don't define any other words, and that shrinks it. And then we'll try to find the smallest one. And then we did that with graph theory. I was a non-mathematician. They were doing all the technical stuff.
Okay.
And
And how
then,
long?
and then we found out that the words in the minimal grounding set are first of all, more frequent in the language, significantly more frequent than other words, much more frequent. Second of all, are learned younger, so that fits with the fact that they're grounding words. But the correlations are not huge. I mean, there's a huge number of words there, and finally, there's some relation to whether the word is concrete or abstract, whether it's this apple Charlie in my hand, or apples, or fruits, or edible things, or objects. That hierarchy has something to do with it, but it's not clear yet what.
Okay. And you also mentioned about grounding, and I was wondering if you could go into that topic, and I'm sure it'll lead into the symbol grounding problem, which was your PhD dissertation, if I'm not mistaken.
Well, no, yes, it was. It was, but it's funny to call it a PhD dissertation. It was already. I did. I Everything was. I didn't do it the way people should do it. Everything was done in the wrong order. I should not have been an editor of a journal before I got my PhD. Right? But anyway, yes, it ended up. I gathered some published articles, and that was the PhD dissertation. Um, the the way that I got to grounding was through categorical perception, which is yet another thing, right?
Mm-hmm.
There's an effect that happens, a perceptual effect that happens when you learn a new category. I mean, everything, let's just talk visually. And everything we've seen since we were 4 years old, since we could open our eyes and everything went into focus. So the world has looked roughly the same to us since then, but there are subtle changes that do occur, and when you learn a new category, the Whorf hypothesis says that everything that we see is categories that we learned. Well, that's not true. And your other question about innate categories I answered that. I said, no, a lot of them, like colors, lots of people use colors as an example of a Whorf effect, which is you learn the names of the colors and then you learn to see them as red, orange, and yellow. And if you're in another language community and you don't have a different word for blue and green, for the category blue and green, bleen, let's say you have bleen, then you wouldn't see the difference between blue and green. Well, that was false. You already have the feature detectors for blue and green. You learn the name of a category which is basically blue or green, and we call them bleen. Okay. So there was an effect there, and it was an effect in language as well. Categorical perception originally came from language. Phonemes like ba, da, and ga are kind of like red, blue, and green. If they're on a continuum, and so is red, blue, and green. They're on a continuous variation in frequency or in wavelength of light. And yet we see these bands that look different. And it's called categorical perception in the case of color. And you have the same thing with some sounds, speech sounds actually, ba, da, ga. You can put them on a continuum, and yet you'll still feel a qualitative difference when you pass from one band into the other. That effect and the attempt to produce that effect from learning rather than from innate category detectors was what finally indirectly and sort of incoherently led to the symbol grounding problem. Because when you learn a hard, this we found out experimentally, if you learn a hard category, not an easy one, if it's black and white, you can probably teach black and white to a kid just from a couple of examples, because we already have feature detectors for black and white. But we don't have feature detectors even for it's, although it's still very easy. We don't have as feature detectors for orange or tomatoes and apples, red apples. I mean, red apples and tomatoes are both red, round fruit-like things. So we have to learn the features that distinguish apples from tomatoes. With apples, it's easier because they can come in other colors, and tomatoes are softer and they taste different and all that stuff. So, but that's an easy category. I'm not sure whether that would give you the effect that I was interested in. I was interested in learned categorical perception, where as if the rainbow starts out as shades of just continuous shades of wash. You don't see red, and then eventually the bands come out once you learn them: red, orange, green, blue. Well, with much more unfamiliar categories, textures, Fernanda, whom you remember, Fernanda Perez-Gray, okay, was able to show that in the beginning there are no categories. It's like the shades of gray. It's a bunch of textures that vary. They look like little black and white bits in
like QR codes.
Yeah, like QR codes, exactly. But if you are trained by supervised reinforcement learning to identify some QR codes as lacamites and some other QR codes as calamites, and in fact, you partition the space so we're only talking about dichotomy. So all of the space of QR codes is separated by certain features that we experimenters as gods pick to distinguish the lacamites from the calamites. In the beginning, the participants have no idea. And some of them, even at the end, have no idea because we only give them an hour of training to learn it. We've gone on since your day to do it for weeks, and eventually everybody learns it, but some people take a much longer time. And what happens is for those who learn it in an hour, that's enough, actually, who learn enough of it. We no longer even talk about those who learn it and those who don't learn it. We talk about the degree to which they've learned it, which is simply the percentage that they get right. And during the hour, they get better and better, so they're getting a larger and larger percentage. And at the end of the hour, we test them. We test them before they start learning, when it's just a bunch of textures they've never seen and they all look alike. And after, when they've learned what the lacamites and the calamites are, to see how well they can tell apart lacamites from calamites. One simple way of doing it, and in your day we did it, was simply give either two different lacamites, or two different calamites, or a lacamite and calamite, and ask the subject to rate on a scale how similar they look. That works pretty well, and that already gives the effect. It turns out that before you learn the categories and after you learn the categories, the differences have changed. The differences between Lacamites and Calamites, which you rated. So some Calamites are more like, so, some pairs of barcodes, or what did you call them? QR codes. Some pairs of QR codes are more similar when you don't know anything, and some are more different. So there's variation there. But what happens is those QR codes that are in different categories, once you've learned the categories, in other words, Lacamites and Calamites, they are rated after having learned the category as looking more different. And within categories, two Lacamites or two Calamites, they're not the same, but they're either don't change or they shrink in the differences. This effect has also since been found in neural networks. If you give them the same stimuli you give to human subjects, once they learned it, in their internal representations, this is going to be just words, so I'm not going to show you any figures, but the same thing happens. You get red, you get blue separating from green. In the beginning, it's all a wash, and then they separate. So that made us think that maybe that's what happens when a category gets grounded. First of all, you learn the features, and the features act like a feature detector that makes the world, that makes the stimuli look a little different. It's when people look at the people who have gone through our experiment with textures, they don't, every time they see a texture, they don't suddenly see them as Lacamites and Calamites. The difference is very subtle, and it's only when you restrict them to QR codes, and then you give them a sample, you find that they can tell certain QR codes apart better after they've learned Lacamites and Calamites. So that's it. And that's the short story. And the idea is that that's the way symbol grounding works. When we reduce the dictionary to the minimal grounding set, there's still the question, okay, fine, that's the smallest number of words from which I can get to all the rest of them. But how do I get the meanings of those words? And the answer is by direct sensory motor supervised and unsupervised learning, or with innate feature detectors, if you have them already.
Right. So, in essence, you're arguing that to experience grounding, not an experience, that's a weasel word, but to have grounding, you need to have a body. Is that what you're saying?
Yes, because in order to, what we're grounding is names for things outside in the world. I mean, right? We're not large language models. In fact, we should talk about ChatGPT because it's relevant, right? We're not that. We're not a word pusher like ChatGPT, and moreover, we're not a word pusher with a huge feed of words. In 2021, ChatGPT swallowed huge chunks of the literature the way our brains will never be able to do it. I mean, there were more words squished in there than we'll ever squish into ours. But ours get in there after we remember categorizing is learning what's the right thing to do with the right kind of thing, and naming it is just one of the things. And we now know why it's so important, because once you've managed to tag them with a name, and you've tagged the features with the name, then in principle, it can all be language words afterwards. But we have to get there. And so the idea is that what we did in the laboratory with Lacamites and Calamites, and we've done with other kinds of stimuli as well, is what happens in the real world when the child is learning a language. But before the child learns a language, the child has already learned a whole bunch of categories. And for the ones that it's learned just by trial and error without naming anything, but just doing you don't have to, in the experiment, the response is Lacamite or Calamite. But on the island, the response is eating it or not eating it, right? So kids are doing a lot of that. And they've got the categories. They're ready. If somebody comes to the island and speaks English, and you've learned which ones are which, you can tell them in words that the edible mushrooms are the black and white striped ones with the red caps, and the rest of them are all poisonous, right? You can tell them that, and then they say, okay, fine, those are the edible ones. They can label it with. I mean, edible they've already got, but now they know that those are the edible ones. But for example, with zebras, for example, once you've told them the black and you see a bunch of horses and zebras, and you say the black and white ones are called zebras, and then you say, okay, I know what black is, I know what white is, I know what the horse looks like. I know that now that you have to call them zebras.
Okay. And so you also mentioned that the symbol grounding problem is a problem. And can you go into why it's a problem?
Uh, well, I more or less did. I said if you're in a that's what the dictionary is meant to tell you. This you can get all the definitions, but you still don't understand the meaning of a single word unless you have grounding at least for the minimal grounding set. And that minimal grounding set cannot be grounded by words. That will just it would continue to be squiggle squaggle dictionary. You have to ground it by finding things in the world to which those words refer and learn
Mm-hmm.
that are categories and learning the features that distinguish the members from of the category from other categories with other names. See? So that's the symbol grounding problem. How do you do that? And the solution, at least one can't, underdetermination is relevant here. There may be more solutions, but one solution is what we do in the lab, which is to teach a, a sensory motor body to, to detect the features that distinguish the Lacamites from the Calamites. And once it's done that with 1,500 categories, or the right 1,500 categories, it doesn't need to keep doing that in principle anymore. The rest of it can be done with the magic. The really magic thing is language, not ChatGPT. And ChatGPT is profiting from some of the features of language,
Right.
grounded language. Because for everybody who uses ChatGPT, whenever he tells you something you didn't know, unless he uses words you don't know yet, and then you can ask him what those are, and he's like a dictionary too. He is grounding new categories for you verbally, indirectly, the way we do for one another, the way I hope I'm doing to the people who watch this video or listen to this podcast, right? That's the
Okay.
magic of language.
Right. Okay, so you mentioned ChatGPT, and I'm sure there's a whole host of things we can talk about. But firstly and foremost, how is ChatGPT not undergoing some type of grounding process? And the reason why I say that is because it does deceive you a little bit. It does say, I understand what you're saying, or I understand the question, or I don't understand the question, but it doesn't
Yeah, it does. But
understand.
if you probe it on understand, it comes back because you've been trained to do it. I don't understand anything because I'm not grounded and I've not been out in the world. That's not because GPT thinks anything. It's because
Mm-hmm.
the way it's been shaped to respond to that kind of question is to say that kind of stuff. So go back to your GPT and probe him a little bit. He'll tell if you say to him, "Do you understand? What do you mean by understanding? Do you understand?" And whatever he says in the end, he's going to say, "But I don't understand because I'm just a bunch of words. I'm a bag of words and some algorithms and parameters."
Okay, okay. And following up with that, how can ChatGPT uh, kind of probe us into understanding cognitive science, specifically in the way that you framed it with the Turing test, or as
I
others
haven't
might know it,
talked
the
about the
imitation
Turing.
game? Yeah.
I haven't, no, I haven't talked about the Turing test. Do you want to first ask me what that is before we talk about
Sure,
it?
sure. What is the Turing test as you have defined it?
It's not an imitation game.
Right.
The Turing, when he defined it, called it the imitation game, but he didn't mean it. You have to believe me, he didn't mean it. He meant what we eventually take to mean by reverse engineering, to figure out how it is that the brain can produce all of the things we can do, including talk. And the test was going to be that once you've got it talking, able to, you give it the ability to talk like we can, to the point where we can't even tell it apart from a person, uh, it's past what we called in class T2, the verbal version of the Turing test. But there was something missing there. And it's not Turing when he decided that, when he proposed that test, it's not Turing who missed it. It's all these people who are missing it now. And when I wrote that article about the symbol grounding problem, it was it got cited an awful lot. It's the most cited article, but I'm not looking at the citations anymore because they all get it wrong. It's really disheartening to hear how wrong they get it right to today. And it's up in the air again with ChatGPT, and people are getting it wrong again. Not all of them. There's some people who are finally getting it. The key word was to ground it. It's got to be sensory motor. You can't do sensory motor um, grounding with a bag of words and a bunch of computer algorithms. You
Mm-hmm.
need to have a robot. A robot is not a computer.
Right.
A robot has sensors and effectors, which are not computation. They're physical devices. And we are robots of a special kind. We're alive and we're sentient. And the reason I don't eat animals is because I don't eat sentient things, because we don't need to. So we are alive and we're sentient, but we're still mechanisms of some sort. So let's call it, frankly, we're machines. Turing was arguing that a machine could do everything we could do. He, he, I don't, unless you want to get into computation, I won't. But
Go for it.
you want to? Okay. Well, in the original paper, when he suggested the so-called imitation game, which is really just reverse engineering, he was talking in the same breath about two separate things. One of them is what the Turing test is about, which is have I built a device that is capable of doing everything a human being, a normal human being, an average human being can do, not just talk. The assumption is if it says apples are red, it means what it says, and it can tell, and it can pick, and it can recognize an apple. It can not only describe an apple. ChatGPT can say apples are red and can tell you what red is and what apples are, but those are just words. Can it actually connect to the referent of the word apple, and the fruit and so on? So where was I going? The Turing test was about that, but Turing is famous for many things, and another thing he's famous for is the Church-Turing conjecture, which is that what mathematicians do when they're doing mathematics is computation, and the computation is just symbol manipulation, which is what a Turing machine does. It takes symbols like X and Y and 2 and 7, etc., and it manipulates them according to a recipe, a formula, to come out with a response, an answer. And the weak Church-Turing thesis is that that's what mathematicians are doing when they're computing. They're manipulating symbols according to a rule for what to do with what symbol. Let's call them squiggles and squaggles. A simple version of what computation does is if you get a squiggle, put it down and pull a squaggle. Okay, that's just manipulating symbols, right? And that's what mathematicians are doing when they're doing mathematics. But there's a stronger version of that thesis called the strong Church-Turing thesis, which says not only is computation anything and everything a mathematician can do and prove, but it also can this is imitation, simulation, or it can simulate or model anything in the world. That means apples, not just words about apples, but it can also simulate apples, and it can simulate ice cubes. I'll use ice cube for a good example. You can do a computer simulation of an ice cube. What do I mean by a computer model or a computer simulation? By symbol manipulation alone, if you put in the right recipe, which is an algorithm, which captures just with squiggles and squaggles all of the relevant features of apples and interactions with apples, then you have a model of an apple. And the model of an apple is so good that in principle you can feed it into a virtual reality machine, a virtual reality machine, which controls your goggles and your gloves. And with the ice cube, for example, you can say, look, do you see that ice cube on the table? And there's an ice cube on the table, and you can reach forward and you can pick up the ice cube and you can hold it and you can see it melting in your hands. If the virtual reality is really good and it can do, and the gloves have temperature sensors, it can make it feel as if your hand is getting colder and colder as the ice cube melts. But that's all an illusion. To see it's an illusion, you just have to take off the gloves and the goggles and you see nothing there. And in the other room, all you have is a computer that's doing squiggling and squaggling. So the strong Church-Turing thesis is that computation is so powerful that it can simulate just about anything. And it's not just for fooling you in virtual reality. You can simulate things for or model, because it's the same thing to model. You're reading these days all the time when we're talking about COVID, for example. We're talking about according to the current COVID model, which is undetermined. It's not perfect. We predict the following for the following reasons, and if the model is right, it will make the right predictions tomorrow, right? So, and if you build, for example, you have a rocket. The example I used in your class was, if you have a rocket that can do certain things at a certain speed under certain conditions, but if you get into certain kinds of atmosphere, it starts wobbling, okay? And it needs to have that corrected. One way you could do it is to keep on building more and more rockets and trying them, but that's expensive, and and it could take forever. Or you can model the rocket to the best of your ability and also simulate the conditions that cause the wobbling and see what you have to do to the rocket model to make it stop wobbling. And once you've figured out in the model to what to do, then you can build a real rocket using those principles. And that's how modeling, computational modeling is being used these days in everywhere, in physics, in biochemistry, in medicine, and everything, okay? And that's the strong church Turing thesis. The Turing test is about whatever it takes to get a robot to be able to do what you and I are doing now, approximately, indistinguishably from you or me. Not just to talk like us, like ChatGPT, but to connect what's the saying? Put your money behind you, whatever. Cash in the words by showing that you really know what you're talking about. When you say, right, when you say the robot, the rocket wobbles, you should be able to not only say it, but you should be able to recognize the conditions in the world where you have wobbling in the robot, right? For example, visually, and tons of so. I don't. You heard the interview on gradient, so you see how I talk, and you've taken my class. So I don't know what your listeners have followed from what I've said. You're following it because you've had a lot of indoctrination.
It was very welcome indoctrination for one. All right. So one thing that you mentioned in the Turing test is T2, but it's not a spectrum. It's a grade, right? So can you define what T1 is, all the way ranging to T5?
T1 is a toy. It's not the T test at all. It's a chess playing computer program. It's not. It can't do anything. You can hardly do anything we can do. It can play chess. I can't even play chess, so it's playing something that not everybody can do. That's T1. So you get into the Turing hierarchy with T2, and that's words only, because that's the one that Turing used. And the next one is the The robotic version is not just words, it includes words. The robotic version of the Turing test is indistinguishable from us, not only in what it says, but also in what it does and what it does with what it says. That's the robotic version. And then there's, I don't know if you want me to get into T4, there's also what's going on inside the head. But most of us, when we think about cognition and what it is, what you're able to do if you can think, cognition is thinking. We think about what we can do, not what's going on in our, if we had the robot in the class, somebody who pretended to be a robot, and the idea was if she opened her head and showed that there were all kinds of other stuff there that's not in our heads, that would make us wonder. But it's not clear how relevant that is. Mm-hmm. I would say that T4, which is what you can observe of what the brain is doing, but not out in the world and not verbally, but inside its head. The only part that's relevant, I think, Steven says, I think, is what needs to be put into the robot in order to make it past T3. In other words, without certain T4 features, maybe it can't pass T3. But we'll learn that in trying to get it to pass T3 and then fishing around with T4 features of the brain and trying to build those. For example, I think it would be a good idea to build in the capacity for supervised and unsupervised learning, which we know you can do computationally. and the brain can do it. But not necessarily with the same physiological apparatus, but something like that. And I think probably there's quite a bit of analog computation that the brain is doing as well, which is not, it's not Turing computation. It would be a good idea to use that to reverse engineer T3. But in the end, the goal, in my view, is T3. Whatever gets T3 passes, and then you've reverse engineered cognition. You've given a causal model, just like you have with the rocket. Um, Not only do you have the computational version of it, which is not relevant, really. I mean, that's the strong Turing thesis. But when you turn the computational version of it into a real robot, it works. I mean, it's supposing it was me, supposing I was the one that said it was 5 years ago in MIT that was built.
Okay. And so, um, so reverse engineering cognition is, you say, the purpose of cognitive science, and I would
Yes.
agree as well. What are the exact like methods that we're going about to reverse engineer cognitive science? Because it is a immense task if you think about it.
Being a vegan, don't expect me to recommend that you start cutting up the heads of innocent sentient creatures. But there's a lot you can do with the head of humans
Mm-hmm.
without cutting anything up. And the fact is, here at McGill, they, not me, because I was already a vegetarian, they were doing things with animals way back 60 years ago that now it's a piece of cake to do it with a human being with non-invasive mental imagery. And they never found anything out. I mean, there was nothing that they found out that we couldn't have found out this way, or almost nothing. There may be some. Remember, we made a distinction between cognitive function and vegetative function.
Mm-hmm.
Vegetative function includes, digestion, growth,
Heartbeat.
immune system, etc. Medical things. On medical things, I personally say I'm satisfied with medicine as it is now. Don't hurt anything to save me. But I can't say that it's wrong to do that. I mean, parents will have children who have terrible diseases, and it may be that you have to hurt animals to be able to cure their kids. Rarely, I would say 95% of the research in every area, including in cognitive science, is junk. It's you throw it away, it's not going to help anybody, it's not going to lead anywhere. But maybe 5% really will. And I haven't got the heart. I'm a vegan because I have a heart for animals. I haven't got the heart to deny humans that. I have no problem telling them that you don't need to eat meat to be healthy and survive. But medicine is another story. So for cognitive function, peeking and poking won't help at all. I mean, telling you where in the brain what is going on will not answer how it's being done. Reverse engineering is trying to figure out how it's done and why it's done, and the why comes from an evolutionary explanation and not from a biochemical. I mean, yeah, not just causal function here and now, but causal function in prior generations and what led to it. Okay, so the methods that I think work, surprisingly, because a good part of the course was also showing that what's going on in the brain and what it takes to reverse engineer cognitive capacity is not just computation. So it's not just computation. There are other things I've already said. Sensory motor interfaces themselves are not computational. They have to be physical. And lots of analog things, lots of biochemical things, for example. You can synthesize dopamine. Pardon me. You can simulate dopamine, the properties of the molecule, et cetera, et cetera. But it's no more the molecule than the simulated ice cube is the ice cube, right? So what I'm saying is there could be real ice cubes in the head. I don't really mean ice cubes, but there's stuff that could be going on in the head that is real ice cube. And we have to figure out what they are. Computation is still the best way to do it. Even in his famous Chinese room argument, Searle said that what I'm criticizing is computationalism, which is the theory that cognition is just computation, nothing but computation. well, sorry, he said that cognition is computation. And then he did his argument that in the Chinese room you wouldn't understand Chinese even if you were passing the Turing test in Chinese. Did that go by too fast, or should I
Can
actually
you
do
explain the
okay, okay.
Searle's Chinese room argument?
Yeah, it doesn't, the fewer words you use, the better it is. He said something like what I eventually said afterwards with the Chinese dictionary. He says, supposing you had a a candidate that could pass T2, which means it could be a chatbot with you for a lifetime, indistinguishable from a real person. You could not tell it apart from a real person. Uh, and supposing it did it purely by computation, this is important. He says, just a computer can do that. Searle, because of the nature of computation, could do the same computations. I could find out what recipes it's using, and I could take the Chinese. If you're talking to it in Chinese, I could take the Chinese inputs, which are symbols, and I could manipulate them according to the rules, and then give you the output without understanding anything that I was saying. You may have asked me what does ban ma mean, and the answer may have been it's a striped horse, right? I wouldn't know that I was saying that in Chinese. So if I wasn't understanding it, then the computer doesn't understand it, and therefore cognition is not computation. He said it too strongly. He said it's not computation at all. Go study the brain. Go bugger up a bunch of animals and do a lot of mental imagery. But the answer is that all he's proved is that it's not just computation. A lot of it can still be computation. And he called computationalism strong AI, the strong artificial intelligence, the theory that cognition is just computation. But in fact, he endorsed, and he was right to endorse, weak AI, which is the same as the strong Church-Turing thesis, namely, the computer is a very useful tool for testing theories, for modeling, etc., as we did with the rocket science. And so that part was right. And I still think that that's going to be the biggest component. We're going to be finding out, first of all, we don't have an exact idea of what it is that humans can do, but we have a good enough idea already that we've got our work cut out for us for a long time. You don't have to do the fine tuning on a particular cognitive task before you can start doing modeling for heading towards the Turing test. We already know enough, but doing in our work, for example, it turned out to be useful to have a computer model of supervised learning and to be able to put into that computer model of supervised learning the stimuli that we give to our human participants to see whether just in the stimuli themselves, there are some that are harder to tell apart and less hard to tell apart, because that we could do with the computer model. Okay, and stuff like that, it's still useful for. But in general, it's gonna require ideas. And in fact, you said weasel word without defining it. A weasel word. Do you know why a weasel word is called a weasel word?
Because
You know,
you can use it to weasel your way out of defining
yeah.
anything.
That's the metaphor. But why is it called? What's the weasel got to do with it? Yeah, no, it's not. No, it's not that. I thought it was that too. It's not to weasel your way out. It's because weasels, who are carnivores, but carnivores. When I was vegetarian, I also ate eggs and dairy, and now I don't eat them. They eat dairy. They eat eggs, and what they do is they nip off the end of an egg, just nibble off, and then they suck out all the egg, the white and the yolk, and then leave the egg. So the egg has the shape of an egg, but it's got nothing in it. That's why these are called
That's
weasel.
a great metaphor, actually.
Yeah, it's a really good metaphor, except I don't like it because it's not very visual. Um, anyway, so what was I going to say?
You were talking about weak AI and and Chinese room argument.
Yeah, I've done that. What I was saying was that in the process of doing
We were
computer
talking about
model.
reverse engineering cognitive science and weasel
Yeah,
words.
that's the name of the game, reverse engineering. And you asked me I'm not an oracle. How are we going to do it? You have no choice but to do it with our brain, right? We're not going to be able to we're not going to be able to read it off the functioning of the brain by peeking and poking and figuring out what's going on where. That is, it's like an NP complete problem. You can keep on doing that forever and you still won't. And in the end, of course, you can clone the brain, but then you still don't know how it works. All you can do is duplicate, right? So to figure out how it does it, you're going to have to use your own brain, and you're going to get a lot of things wrong. And the people that read my paper, The Symbol Grounding Problem, got it all wrong. I mean, they didn't even understand what the problem was. They kept coming back with ungrounded solutions.
Right.
And yet, I can't go figure, because I can't figure out why, because it seems to be simple enough to say sensory motor function, you dummy, not simulation of sensory motor function, but sensory motor function is what it needs. You can figure out what sensory motor function, what features of sensory motor function are needed to do it in simulation mode. But a simulation, one of the answers to Searle that they used to give was, okay, fine, it's not a robot, but you can connect the thing that passes the T2 to a robot, and then you've got a grounded robot. Nonsense, nothing of the sort. And then the other answer, that was the robot reply. And then the other answer was, well, you can, because it's Church Turing thesis, you don't need to just pass the T2. You have to add in a simulated brain, right? So more squiggles and squaggles, and then that'll be the right answer. But nothing of the sort. I mean, then you'd have a chatbot and a simulated brain, and nothing. I mean, it's still not connected to it still doesn't do what T3 does. So the answer there, for dummies, was it's got to be sensory motor because of T3, and T3 has to be robotic, and a robot cannot be just symbols. But there's still a hell of a lot you can do with symbols. I mean, the reason I start with praising computation before I start kicking computationalism is because you have to appreciate how much computation really can do. It's enormous. Right. It's a nuclear weapon. There's something that's even more powerful. What is it?
Language.
Yeah. And that's the interesting thing, that computation is just a subset of language. It's a syntactic subset of language. It's a thing that you can do with symbols, ungrounded symbols, right?
Right.
But it's useless as long as all you have is, I mean, a computer, if you set a computer loose on the world, it can't do anything. You have to have users that can interpret what it is that the computer does. And so, so a second thread that I lost, because I've come in and out of so many things that so once you've realized that your task is to pass T3, real T3, throw all those citations of the symbol grounding problem into the garbage if they're trying to do it with symbols alone, including everything on large language models. I mean, everybody's come out and saying, yeah, they really are grounded. They conveniently leave out the word symbol, and they conveniently leave out the word sensory, but they somehow picked a metaphor, a weasel word, by the way, for which they call grounding, which is somehow how are words connected to their reference. But what they end up being connected to is more words. Right. Just like the Chinese dictionary.
It's recursion, right?
Well, it's recursion on symbols. I mean, what it is actually it's infinite regress, is what you mean to say.
Oh yes, that's what I meant. Infinite regress. Yeah. Thanks. Okay. I was holding this question for a while, and I'm just wondering if you could explain this minute distinction. You said that if you cloned the brain of a human, you still wouldn't be able to causally explain how it works.
Listen. If you were trying to become a cardiologist, and you needed to know how the heart functions and what to do with various things, if this is wrong, if you clone the heart, we've already got hearts, okay? And when we torture animals, we take hearts out of them. So we've got hearts in our hands. But the cloned heart is not an explanation of how the heart works.
Right.
Not an explanation. You have to be able to build a model based on a real model. I mean, first you have to simulate it, and then you have to be able to build a real. Remember, there was a transparency showing a Turing test for the heart. You had a artificial device, but that it could do what the heart does. It can pump the blood,
Mm-hmm.
right? Once you've got that, if that's all the heart does is pump blood, you've got a causal explanation. You reverse engineered the heart. With the human, the equivalent thing is once you've got a robot that can do everything we can do,
Right.
right?
Which is
So
quite a complex task, actually.
but it's certainly not going to be. You can't do it in symbol land. You
No.
got to get out of symbol land. People want to stick to symbol land. They're really computationalists at heart. They don't realize it. They mix up. Oh, listen, we talked about the matrix. They mix up reality and virtual reality. They start to think that maybe I am a computational state in a virtual reality, which is complete gobbledygook, complete garbage. It gets everything mixed up. But what can you do? If you start thinking that way, you can't stop.
Right. It's kind of like we're entering some form of solipsism in
It's
that sense.
solipsism. It's solipsism, but I mean, we are solipsists, and we're right to be solipsists. The only
Mm-hmm.
one that can feel, that knows that I can feel, is me. Nobody else knows if I feel it. And if I feel a toothache now, I feel a toothache. I can tell you I feel a toothache. I may act the way somebody does when they have a toothache, and you might be able to correctly infer that I probably have a toothache, but that's under determination. You're guessing that I have a toothache, and you're probably right, but you can't know it. I
Mm-hmm.
can only know it. Okay, so that's solipsism. Uh, the 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 what I call the virtual hall of mirrors that you get when you start projecting meaning onto a symbol system. You so project it from your own head, where you have grounded meaning, you project it onto a symbol system, a computation, and then from what you get out, you re-inject it, and you think, aha, I understand, and it understood. If it was a good recipe that it was working on, like ChatGPT, it'll give you something that really is right, but it doesn't know it's right,
Mm-hmm.
and it certainly doesn't know anything. It doesn't even know what an apple is. It
Right.
can tell you what an apple is, but it can't do the right thing with the category.
Correct. Correct. I do have this question about ChatGPT. So you have this paper called Post Gutenberg Galaxy: The Fourth Revolution in the Means of Production of Knowledge, where you argue that the internet is a Gutenberg-like invention, and you say that the first revolution was the invention of language, the second revolution was the invention of writing, and the third revolution was the Gutenberg press, and the fourth one being internet. Do you believe that ChatGPT is either the fifth one or approximating a fifth kind of revolution?
It's part of the fourth. It's part of the fourth.
It's part
Uh,
of the. Okay, interesting.
right? I mean, what ChatGPT has done, it's taken the whole of the, not, I'm exaggerating, but the whole of the internet and swallowed it. And it's made itself into the chatbot of the universe. Ask
Mm-hmm.
me anything, I'll tell you anything. That's a product of the fourth revolution. But there is something going on, and it's not in that series of revolutions. The revolution that started with language had a lot more happened there than we realized or even realize now. And ChatGPT is beginning to give us an idea of what power there really is in language. I mean, grounding theory already said once you grounded 2,500, 1,500 categories and named them the right ones, you can do everything else with language. That's already a nuclear weapon there.
Mm-hmm.
But when you're there's something else the chat GPT is getting from the immense blob gulp. I call it the big gulp in 2021 when it swallowed all that stuff that we couldn't possibly swallow, which is just a word bag, a huge word bag plus algorithms for extracting information from it and for aligning things, etc. So it's basically a word bag plus computation. What it got out of that was more than I would have thought was in there. It was bigger than a dictionary is in a sense also a kind of a complete word bag, because every word in a dictionary is defined by words in the dictionary. That's sort of self-contained. That word bag is beyond that. It's not just dictionaries, it's textbooks, it's manuals, it's courses, it's whatever anybody said to anybody else ever that was true or false. All of that, it's got, right? And it can, and the manipulation of, well, I don't know how actively OpenAI keeps a few secrets. I don't think these are important cognitive secrets. Maybe I'm wrong. What we do know about it, we already know. We know about how it guesses the next word, how it's trained to maximize the probability, how it keeps statistics on what co-occurs with what, how it gets parameters, how it puts it into a vector space with distances. We know all that stuff, and we know with that it produces stuff nobody expected. It was written to summarize stuff that other people had said, and it does that, but it can do more with it. It can generate new stuff out of it, sort of new stuff. Is it really new? It's not clear. I mean, ChatGPT has been accused by, I guess, Emily Bender of being a statistical parrot. It's clearly not a parrot. If it were a parrot, it would have echolalia. It would say what we say. It would just repeat what we say. It's obviously recombining stuff. How is it recombining it? It's combining it. It's recombining it under the help of the under the help of the. Whoops! Stop raising my hands. Under the help of the big gulp, which it's got in its belly, and at its fingertips or whatever all the time. I don't. It's distributed in computers all over the planet, but it's effectively all accessible to it. And to a certain extent, it's accessible what you've just said to it, but not as well. It's out of the combination of all that stuff that it generates new combinations, right? I mean, they're not new. It's recombinations of that stuff. Now, I don't know what I'm saying when I'm saying it's just recombinations of that big gulp, because what we do is largely just recombinations as well. And we can't forget that. But there's more to it. We're doing, and this is where grounding comes in. We are doing grounded recombinations, not just word recombinations.
Right.
When I combine text written by someone else, I carry with it you never leave your grounding. You never really get off the ground. When you get higher and higher, when you get to the point where you've got your 1,500 words that are grounded directly, where if you say apple and you've got your image of the apple and you've got you can say the feature of the apple. Once you're up to pterodactyls, the dinosaurs, you got there from apples, and immediately before it, there are words like dinosaur and animal, etc., which are getting closer and closer to the ground, and they're carrying their sensory motor grounding with them, their categorical perception. Those changes in the way that the world looks because you learned a new word are still there. They're still, and all this nonsense about we do cognition by imagery, we do cognition by verbal stuff in our heads. That's not the explanation. Those are just things that we're aware of while we're introspecting. But it is true that we are carrying that baggage with us when we're upstairs. We never leave it alone. We're never flying. We're always basing it on that. So that's what ChatGPT lacks. And I would have predicted that because it lacks it, it could never even do what it really does do. So it turns out, even though it's not grounded, and grounded only means, for all users, it means sensory motor robotic grounding, not whatever the literature is saying now, and whatever ChatGPT already misuses the word grounding, because in his big gulp, which was in 2021, that was already long after 1990 when the paper appeared. So it had been distorted monstrously. The way, if you look at a Wikipedia article, the way it gets distorted once a bunch of know-nothings start trying to get more airtime by changing things about stuff that they don't understand. So it's been tremendously distorted, but it's lacking that. And I would still be wrong if I said that what's lacking is sensory motor grounding, because there's something else that's going on there. And it's not, and it is happening in wordland. It may be partly dependent on sensory motor robotic grounding, but there is more. Remember in the course, we talked about what a symbol is, and a word is a symbol too. So you have mathematical symbols and you have words as symbols. It's just an arbitrary object, a squiggle or a squoggle that you use, an arbitrary shape that you use to manipulate other symbols, other arbitrary shapes. But if the recipe that you're using is the right recipe, then what comes out will make sense. Okay, and you can make sense of it because you don't just see symbols. You also have a mind, and you can interpret the symbols. So you know why you are using that algorithm. You know what some bits of it mean to you, right? Not to the algorithm. And that guidance that you have is not related to the shape of the symbol. As I said, that the symbol shape is arbitrary, but it might be related to the shape of the proposition. Now, and we couldn't have said this before ChatGPT. The difference between cat, which is just the name of a category, cat, and you can pick out cats and you can stroke them and you can feed them, etc. You do the things that you do with cats. You protect them from predators and things like that, and you don't eat them, or any other sentient creature. A cat is not shaped like the word cat or sha or mochka in Hungarian, or what is it in Slovakia?
Machka.
Mochka. Yeah, right. So you recognize mochka.
It did, yes.
But it still doesn't look like a cat at all. Right. But proposition and the cat is on the mat, which is a proposition, also doesn't look like a cat. Or it doesn't look like a cat on a mat.
Right.
Cat doesn't look like cat. Mat doesn't look like mat. On doesn't look like being on something. And cat is on the mat doesn't look like a cat being on the mat. But ChatGPT has another perspective on this, because ChatGPT has in its repertoire the cat is on the cat is on the mat. The mat is on the cat. The dog is on the cat. The mat is on the mat is on the cat. The mat is on the dog, and every other word you can say. And those are constraints that help it not only in recombining words, but in sifting out which words not to be recombined, because there isn't the proposition. To pick a Chomsky word, a sentence, there's the proposition. John is easy. Yeah, John is easy to please. John is eager to please. That's all fine. John is eager to please Mary, but there isn't John is easy to please Mary. That would be an error in universal grammar. ChatGPT makes no errors in ordinary grammar, but only because most of what the chat. I think if they had left the swear words in and the racism, etc., maybe they would have gotten more agrammatical ordinary grammar errors from ChatGPT, but they sort of censored them out. But everything, including the ordinary grammar errors, is not a universal grammar error. There are no universal grammar errors in any of the big gulp. And we know that people don't produce grammatical. Maybe if they had a tremendously huge part of it that was linguists talking about, sort of sitting around a table talking about what you could say and what you couldn't say, maybe it would get a few bits of UG violations there, but it doesn't have any. And so all these constraints on what people do say and what they don't say, and may grammatically, I'm not talking now about meaning, I'm talking grammatically, but may be channeling what it says even in meaning, in when it puts together things for meaning. And Chomsky, and that's just a hunch, that somehow Chomsky goes further. He says, I don't think that the grammatical rules of UG, universal grammar, are in essence, they're not grammatical rules. They're rules for what you have to have in order to have a language that expresses human thought, which is not language at all. And therefore, the sentence, John is easy to please Mary, is not a thinkable thought. You can't think that. There's nothing you can fit that onto that is a thought. And language is really an expression of thought. So what's guiding ChatGPT is not grammar, or not just grammar, but thought, but the constraints on thought.
Right.
I'm not endorsing that, but I'm saying, look, Chomsky is one of the greatest intellectual giants we've ever had. Give his words heed. Turing is too. Darwin is too. So give them their due.
Okay. Well, thank you for that answer. The question was very, very in depth. And so you mentioned universal grammar. Could you define it, what it is exactly?
Okay. I can't define it. I've never taken, as you know, a linguistics course in my life, but I know how to. I can tell. Uh, well, we can all tell a universal grammar violation. We can't tell if it's universal grammar or ordinary grammar because he ain't do that is not a universal grammar violation. It's an ordinary grammar violation. We can detect those. We can usually also say or retrieve why it's wrong. With universal grammar violations like John is easy to please Mary, we can tell it's wrong, and there's an infinite number of them, and we can tell all of them, but we don't know why. And the only ones who really know why they're wrong are the ones who have studied linguistics and universal grammar and partly reverse engineered it. They're trying to reverse engineer universal grammar capacity. And so what was I going to say? So universal grammar is a surprising discovery that Chomsky made. He wanted to know what language was, and he wanted to know whether there was anything that was universal to all languages. And we already know that you and I understand machka or machka, but people who speak English don't know. So vocabulary is not the same across languages. Grammar's ordinary grammar differs across languages. So, but there is something universal about grammar, and it's called universal about languages, and it's called universal grammar. It's certain rules that we never learn. They're unlearned. They're among the universal grammar is an innate category. The thing that you asked about. You are born not able to speak language. We need a little bit of training to be able to speak language. But once we start speaking language, we're born with the capacity to obey universal grammar rules. We are not born with ordinary grammar rules. We have to be taught them, and we certainly make mistakes about them. So they're different. Universal grammar is those rules that all languages must obey in order to be languages. And then universal particular grammars are sort of parametric variations of how you can do that, including ordinary grammar and vocabulary and various other things. That's universal grammar, and it has a peculiar characteristic, which is hidden in what I just said, which is children don't learn it.
Yeah.
They learn language, but they don't learn it. And the reason that with vocabulary, you have to learn, you go through a child's picture book and you tell it, this is a bear, and this is a gorilla, and this is a dog. And then you show more bears and more gorillas and more dogs. And then the child points to a gorilla and says bear. And you say, no, that's not a bear, that's a gorilla. And then it gets corrected. It gets the features. It does the category learning. And in the end, it can tell apart gorillas and bears. In the case of universal and ordinary grammar is pretty much like that. You learn ordinary grammar also by trial and error with correction. Some of it you can learn by unsupervised learning, which is by just being exposed, hearing it often enough, and then you say, aha, I get it. Okay. But with universal grammar, you know it from the get-go. You never violate it. The only ones who ever violate universal grammar are, well, there's two kinds of people, linguists, and they do it deliberately when they're trying to figure out what the rules of universal grammar are, and people who are speaking a language that's not their first language, and they're using the parametric setting of their first language in their learned second language, and it artificially produces a universal grammar error, and they can't tell that it's a universal grammar error. Or they say something that, yeah, for example, a Hungarian might say, I'll say it with a Hungarian accent, John is easy to please Mary. Because in Hungarian, can you, yeah, because the parameters of Hungarian different, and there something that that seems to be a translation of that is okay.
Mm.
But that's only because Hungary has different parameters, and those parameters are all on. I can't discuss what parameters are now, but they're all features of. You have universal grammar, but you have to learn your particular grammar, and that particular grammar sets certain parameters on universal grammar in your first language. When you're learning your second language, it's not, you've got your parameters set already. So sometimes you read those onto some of the forms of the second language, and it gives you these weird errors also. So some second language errors. I learned this from ChatGPT, by the way. I didn't know that. And maybe it's not even true, but what ChatGPT 4 said was that I said, why do children not make universal grammar errors? Why is there a poverty of the stimulus? Why do you not have? Why? How come you can learn the category of universal grammar only hearing members and not non-members? That's like saying you go to the island and your first 4 days all you see is edible mushrooms, so there's no problem, and then you get to the part of the island where there are inedible ones, and now you're in real trouble, right? So how come children can learn language without and speak in compliantly with universal grammar without making any mistakes? It's how come they don't do supervised learning in universal grammar? The punchline is that it's innate in their brains, but the way you find it out is that they just don't make the errors. They just know how to do it right without any errors. And the reason they know how to do it right is because you do need a feature detector, just like you need with red, green, orange, and with zebras. You need a feature detector, but the feature detector is in there, and it's not only innate, but it's implicit. You don't even think it. Just as ordinary grammatical compliance becomes innate. You learn the rules and eventually forget the rules. You have trouble if you learned how to speak English from a grammar school, and then 30 years later you have to teach it to a Gabonese child. You wouldn't remember all the rules. You would follow them, but you wouldn't remember. So you wouldn't be a very good teacher for them, because you need to get all of the problems that they're likely to encounter forward. Because even with ordinary grammar, it becomes implicit, but it can be recovered. Whereas, ooh, my hand thing almost went on. Okay.
It's okay. Well, thank you for that. And just another thing to add. Um, in order for us to reverse engineer cognition, we'd also have to reverse engineer universal grammar
Yep.
mechanisms and functions, right?
Yep. And but fortunately, they're on it. I mean, the generative grammarians are reverse engineering it themselves.
Interesting. Okay. So the last theoretical question I'll ask you, and it's something that I wanted to ask at the beginning, but we kind of glossed over it, which is totally fine. There are two theories of categorization. There's the classical theory, where categories are indeed categorical and some of them are continuous, but there's the prototype theory that argues that categories are all continuous. Could you
You want the short answer? The prototype theory is bogus. It can't do anything. Nobody's working to recognize categories with the prototype theory. The prototype theory says, I figure out what's a zebra, or what's, yeah, I figure out what is a bird and what is a fish by seeing a lot of birds and fish, and then whenever I see a new candidate, it could be a bird or a fish or a turtle or whatever, I categorize it to the one that it's closest to. Each one gets a prototype, right? The typical one, and whichever it's closest to, I classify it for. It doesn't work, or it works for a few really special pattern recognition cases, and it's not done. What's happened is become a weasel word. You use the notion of a typical, etc., for disguising what is really features. What you mean by a prototype is a set of features.
right?
And
So
that's not another theory, that's classical.
right,
You
okay,
have to
okay.
learn that set of features, and you have to learn it by trial and error,
Mm-hmm.
or you have to be told well, if you've already grounded enough and you're in the dark room, you have to be told by someone what the features are.
Okay. Okay. So in some respects, the theory, like its own definition and arguments, kind of invalidated itself.
Listen, psychology is like this, is full of old, obsolete, bogus things. And ChatGPT has them all because they were talked about so much. So if it played a big part in his vocabulary, you're going to get it back. But but he's educable,
Yeah.
right? You can wean him. Not you. They haven't yet built the version where and it would be dangerous to have me fixing up the big gulp, because maybe I'm lying or getting it wrong. But there should be some way of updating it with these interactions, and eventually it'll get updated. So it won't be the 2021 big gulp, it'll be the 2023 big gulp with its own bogus baloney, vegan baloney stuff too.
Right. Right. Okay. Okay. So I have this. I like to kind of conclude my podcast with like a more like loose type of question that's applicable to my guests, obviously. And you've been in the cognitive science and computer science and psychology field for a very long time now, and that kind of in part makes you some type of historian by experience. And I was just wondering, how has the field of cognitive science specifically evolved from when you started researching into it, and where do you think the future could be now? Or not, I don't know, but like in the
When I
future.
started in McGill, behaviorism was already over, and what was at least there was cognitive psychobiology, but they were still doing horrible things, and they still are, in fact. But they still are for biomedical reasons, but for behavioristic reasons that turned out to be useless. Okay, a lot of rats and pigeons and cats and I don't, God knows what else were being tortured because of these simplistic behavioristic ideas, the schedules of reinforcement and stuff like that. That was all for nothing. And already Hebb was there. He also had animals tortured, but they were tortured for things like receptive fields. The receptive field stuff came indirectly out of stuff here at McGill. A lot of stuff came from McGill, in this history, and not just because I came from McGill. Not at all because I came from McGill, but not because I'm referencing it to McGill because I know anyway. Pleasure center stuff came from here. A lot of stuff on early behavior. Even we could even say the Darwinian side, evolutionary psychology, already got a start in those early days in the 60s and 70s. And then a new kid came on. Something that really changed things was artificial intelligence, where we stopped blathering about schedule reinforcement and shaping and stuff like that, or even correlates in the brain. But they started building models, some computational and some robotic, that could actually do these things that until then nothing but organisms could do. And not only do them, but knowing how they do them. So you would say, so I would say, and by the way, Turing's paper was in 1950, which was I mean, I was 5. So it was before I was even at McGill. So it was in the air. But these people were starting to put Turing's stuff into practice badly in the beginning. It was a lot of computationalism. And the next landmark was really Searle, who put an end to this nonsense that cognition is just computation. And then neural networks started appearing, also coming from the domain of computation. They were misunderstood. They were described as being an alternative to computation, but they're not. They're a form of computation. Okay, and then I think I'm really jumping here, but I think the next landmark, even neural nets for all those years, which were doing clever things, but toy things, T1 type of thing, even they weren't getting anywhere until the godfathers of deep learning, Jeff Hinton, Yoshua Bengio, and Yann LeCun in 2015, quite recently, described how it is that they had overcome the limitations of ordinary neural net learning with the multi-layered net and large number of unsupervised. I should talk about supervised and unsupervised learning because that's a take-home thing. Layers of unsupervised learning, and then higher up supervised learning, which turned out to be much more powerful in the same way that ChatGPT using deep learning and then some, and the big gulp. But deep learning itself suddenly broke the boundaries, and it seemed like it could in principle do anything that was learnable. I don't think that's true, but it's a huge chunk of it. And it would be silly of Darwin to ignore that particular possibility. Just as it would be silly of Darwin to ignore the possibilities that the projective geometry give you in vision. I mean, it would be you would have to use some of those things. So I don't think it's the be all and end all, but it's opened up a new world, and ChatGPT is one of the first symptoms of this new world. Mm-hmm. Now, what is unsupervised and supervised learning? Both of them are done by neural nets. The simple version is unsupervised. You want to say it, or should I say it?
You can say it. I like it. Okay. I like hearing your explanations. They're always super simple.
Okay. So unsupervised learning is a neural network is not a graph. It's a network of nodes interconnected that can activate one another, and they have degrees of activation, and they have connectivity, et cetera. The details don't matter. But the perceptron was the first one. I suppose I should have given the perceptron. Whenever Rosenblatt made the perceptron, that should have gotten credit for the switch to neural nets in the first place. I don't know where it was in that series. But unsupervised learning, and I should give a discredit to Minsky, never mind. So unsupervised learning is when you have neural nets that are interconnected like this, and they have an input layer and an output layer, and they're able to produce at the output layer the same thing that they got at the input layer, copy it. Okay, I mean, they have to learn that, but they learn to do it. And while they're learning, you have it could be a sentence, it could be a pattern, anything, and it gives you the same thing on the other end. But the way they do it, unsupervised, and there's no training, no, you're right, you're wrong, etc., is by looking at the correlations between as you produce lots of examples, right? You have to be in a domain. If it's net talk, the way I think net talk was unsupervised, I forget. If let's say you're just giving Slovak sentence, is it Slovak? Mm-hmm. Okay, so you're just giving spoken Slovak sentences, and it's got to repeat them, and in the process it gets better and better. In the beginning, it's garbled, but as some activations get stronger and some get weaker, there is a hidden bit of well, never mind. I don't want to complicate it. By doing it over and over again, some activations will be strengthened and others won't. And they'll be strengthened by the fact that in the stream of Slovak words, there would be certain combinations that occur often and others that don't occur or rarely. So it'll learn it learns a kind of classification. It learns in connection space to put together the things that tend to have the same features and separate them from the things that tend to have different features. That's not categorization yet, because somebody could come in and say, look, that has nothing to do with what it is that the sentence means, and I'm going to train you on meaning, and then you can throw out all of those unsupervised correlations. But it can be useful. It can be, for example, the example I used in class was because if you look at a landscape, you can see, look at landscapes in different countries over and over again, you can't help see that there's some convexities, things that go up like that and down, and concavities, which is, I'm going to activate the hand thing, but the concavities go down like this. So the mountain valley are there. You don't know what mountains are. You don't know what valleys are. You're not giving any feedback, but you do see that mountains tend to have white tops. And I mean, convex shapes tend to have white tops, and concave shapes tend to have see-through tops, let's say bottoms, let's say like lake. That correlation will be picked up by unsupervised learning. And if it's the only thing you need to know in the world, you're already there. It becomes serious when you're not already there, where you can put in all the stuff, but you still don't know what a mountain is, you don't know what a valley is, you don't know what a zebra is. They're all there in the landscape, but you need to pick them out. That's when you need supervised learning. Supervised learning is where you get an input, maybe unsupervised learning makes you give a certain output, but then you get feedback, and then this famous backpropagation. You get feedback, and the connections that are there and the activations, if they led to a correct response, you did the right thing, are slightly strengthened. And if they led you to the wrong response, they're slightly weakened. And that's repeated over and over again. Backpropagation is the algorithm that traces back all of the activation trails that got you to where you are and strengthens the ones that were right and weakens the ones that were wrong. That's an algorithm. It's done in two different ways in supervised learning. It can be done as reinforcement learning. You can say that when the awful people here were doing reinforcement training on pigeons and on rats and on mice, and starving them and giving them food if they do one thing and giving them nothing if they do another one. That's reinforcement learning, except the behaviors didn't know what was going on. There's no explanation of how you give them a reward and they do it, and you give them a punishment and they stop doing it. In these nets, we see that you can have a mechanism that works that way. That's supervised learning. But when you're doing it with a computer, you don't do it the way you do it with animals. You don't do it serially by reinforcement, but you take it's computation. So you take a whole bunch of inputs and you pair them already with their correct output. And if the net, and then you run the computation, if the net gives the wrong output, you do back propagation all at once in batch, not serially as in reinforcement learning, but they're both reinforcement learning. This one is done one trial at a time, and the other one is done all at the same time. That changed the world. And ChatGPT is part of the way it's changed it. And these are landmarks, even though the course was spent criticizing computation, these are landmarks in computation and in algorithms, not in psychology experiments. More progress was being made in psychology, not evolutionary psychology, but in comparative psychology. We're learning, and that's important for me again as a vegan, that we were deceiving ourselves. Not only are we savagely brutalizing and cruelly hurting mammals and other vertebrates that are sentient, and even invertebrates that are sentient. It turns out that octopuses are sentient. They feel. Sentient just means feel. I don't want to use a weasel word like consciousness, awareness, subjectivity, blah, blah, blah. They feel. Well, it turns out that lots of invertebrates feel as well. And so there's reason to change. The most urgent thing is to stop eating mammals and birds, obviously, and the obvious invertebrates, because we don't need to. Because good news, plants don't feel. I don't edit behavioral and brain sciences anymore, but I edit a journal called Animal Sentience. And just this year, just now, there's a multiple peer commentary on whether plants can feel. And some people are arguing that they can, but it's turning out that no, but they can't. But surprisingly, they can do a lot of things. A lot of things that used to only require feeling creatures to do, but apparently can be done by non-feeling creatures. It's a little bit analogous to the way that the first artificial intelligence candidates were doing things that until now could only be done by sentient human beings. Okay, so those are the landmarks for me. I've probably left out others. I'm getting tired.
That's okay. I was about to say this is a good place to stop. And before we stop everything, do you have anything to promote by any chance, like a book or something along those lines?
Nah. I'll tell you, I can give you, there is a series. In fact, you should do this. There's a series of guest lectures on Zoom. It's going to start this Thursday. It's going to go for a year on ChatGPT, grounding, and cognition. You want me to put it in the?
Yes, please.
in the chat?
Yeah, we can do that.
Or no, you know what? I'll send you an email.
Okay, that
So
works.
I'll send you an email of the actual program for the autumn session and with the Zoom connections. Okay.
And when you say for a year, is that like a semester or like for 52
It'll be
weeks?
2 semesters.
Okay.
I'm working on the winter one. Rob Goldstone's going to be talking the winter one, for example.
Oh, awesome.
Dave Chalmers will be in this one. You know who that is?
I
He's the one.
think.
He's the author of the name, not the concept, but the name of the hard problem.
Oh yes, 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 yes. Yeah, that rings a bell. Yeah, I haven't read his book, but yeah, I know who he is now. I remember.
And we've already had one of the godfathers of neural nets, Bengio, last year.
Mm-hmm.
Uh, I'll be giving a talk about ChatGPT's implications for cognition in his series, but I want to invite him back here now because I want to invite him back. And Hinton flatly refused. He's the maybe the main godfather because he profoundly disagrees with me. He's angry with me for not believing that ChatGPT understands.
Interesting. Interesting. That goes in line with your misunderstanding of the symbol grounding problem very squarely, actually.
Yeah, but he's not a Lilliputian. He's a
Lilliputian.
he's a, I used to talk about giants and pygmies, and then I
Mm-hmm.
was told that pygmies was racist, so now I say giants and Lilliputians. I don't think I'm not sure that Jeff Turing is a giant. Uh, um, Hinton and Bengio and Lecan are just very big Lilliputians, but they are very big, and so it's
Okay.
not very big. And there are very few very big Lilliputians today, so that's
Okay. Awesome. Well, Dr. Harnad, thank you very much for taking the time to do this. I really appreciate it, and I will definitely listen to this conversation more than once.
okay. I hope everybody doesn't have to listen to it more than once. I hope it'll I hope it'll be clearer the first time. Anyway, okay, fine. Yes.
Thank you for listening to this episode. To support this podcast, please subscribe to my YouTube channel and rate it 5 stars on Spotify and Apple Podcasts. I'll catch you in the next episode where I talk with an astrophysicist about the nature of the universe. Take care.